here. Everything should be good. Let me get my laser pointer. Okay, so it's good to, well, not to see, but to virtually see you all again. And I want to tell you today about, yesterday I gave an introduction to magic angle bilayer graphene and to the correlated insulator and superconducting properties, as well as some more recent developments that I briefly spoke about at the end of my talk. Today, I want to focus and go a little bit deeper into the physics of magic angle graphene, okay, the importance of correlations and the appearance of a number of phenomena which, magic angle graphene displays a number of phenomena which are typical of correlated materials. These are, for example, competing orders, nematicity. We will see that the compressibility, through compressibility measurements, we can look at phase transitions, and then I'll focus towards the end on the strange metal behavior in magic angle graphene. Okay, all of these phenomena are typically seen in correlated materials, one correlated material or another, and they happen to manifest themselves all in magic angle graphene, which, as you know, is a very tunable correlated material, and hence we can go to different regions in the phase diagram to observe all of these different behaviors. But just in case some of you just joined and weren't present yesterday, I'll do a very brief introduction to magic angle graphene again, just to make sure we're all on the same stage. But before I do that, let me, so just, remind you all that, nowadays we have at least, 3 general platforms to study strongly correlated and topological physics. One is to go to actual quantum materials. Okay, that's the thing that has been done the longest for many decades now, with typical lattice scales of a few angstroms, so atomic scale distances. Then we have also ultra cold atoms in optical lattices. That's something that the community has been doing for about 20 years, where the typical length scale is about a micron. And then we have this new platform, Moire quantum matter, which has emerged in the past 3 years, where the typical Moire length is about the 10 nanometers. So we have 3 platforms, very complementary in length scales, complementary in energy scales, and also complementary in the degree of tunability and complexity that we can reach. Okay. Now, this platform, Moire quantum matter platform, initially was enabled by the possibility to twist 2-dimensional materials on top of each other, is something which people often refer to as Twistronics. Okay, so this twist angle is a new degree of freedom in condensed physics and material science that didn't exist before, and that now we have with the advent of 2D materials. And perhaps it's something that I maybe didn't make too much emphasis because it was the introduction yesterday. Is why would we want to have this new platform? Okay, why Moire quantum matter? Okay, so let me tell you a few points. One is that it's an easy way to obtain isolated flat bands, and you have flat bands and they're isolated. You can investigate the interplay between kinetic energy, interactions, and topology, all in one system. Okay, so the community at large has been looking for flat bands for a long time, and there are a number of quantum materials that exhibit flat bands. This Moire quantum matter is one where these isolated flat bands come naturally, and they're highly tunable. Now, we have that with a few simple building blocks, for example, graphene, hexagonal boron nitride, or transition metal like chalcogenides. These can give plethora of correlated and topological behaviors. Okay, so to some extent, one can get rid of a lot of the chemistry, and with very simple elements and very simple components, we can get all of this correlated behavior and topological behavior. So this brings up the question of what are the key essential ingredients which are needed for complex emergent behaviors of quantum matter. Okay, so this is something that I think plenty of people are interested, to just go to the very basics, what's essential. Now, it's a highly tunable in situ platform. So we have electric field, electrostatic doping, strain, pressure, magnetic field, temperature, etc., and also tunable through the twist angle and the type of Moire system. Okay, so it is really very rich, and we have a very high degree of control. And last but not least, something that is being explored slowly more and more is that it is a novel experimental platform to explore vast new families of hybrid quantum materials based on non-equilibrium growth and assembly. Okay, the type of structures that we're making, you cannot make them if you just grow thermodynamically bulk crystals typically. Okay, so these are non-equilibrium growth assembly of quantum materials, which can display, all of this interesting behavior. And we have just began to scratch the surface of the types of behaviors and complexity of materials that we can look at. Okay, I will show you tomorrow, one example of a next generation Moire quantum matter type of behavior and type of quantum material. Now, as I mentioned yesterday, in this Moire quantum matter, we are, discovering or rediscovering, and in some cases with new twists, pretty much almost all phases of traditional condensed matter physics, or plenty of them, okay, from correlated insulators, superconductivity, various topological phases, magnetism, nematicity and related, Moire ferroelectricity I mentioned yesterday, strange metal. So plenty of behaviors. And today I'm going to focus on this somewhat more exotic types of behaviors and others that I will mention about. So just to remind you all, we're talking about graphene, okay? Graphene is a honeycomb of carbon atoms. The electronic structure has this very unusual linear energy momentum dispersion near the Fermi energy. This energy momentum dispersion can be, written as this, as energy linear in momentum. And there's a pseudo spin here, which in the usual Dirac equation tells you about the spin up or down of the electrons. Here it's telling us whether the weight of the electron wave function is on the A or B type sublattice, okay? And then we have two independent, K and K prime valleys, okay? So electrons in graphene have this fourfold degeneracy, spin up, spin down, valley K prime. Now, if you put graphene on top of graphene, a Moire pattern develops. The Moire wavelength, the distance between the soccer balls here on the screen, can go all the way to infinity for, as you get closer and closer to 0 degrees, okay? And it's roughly inversely proportional to 1 over the twist angle. Now, if in momentum space, these are the energy momentum relations of, the Dirac cone in layer 1 of graphene and Dirac cone on layer 2 of graphene. Their separation in momentum space is proportional to the twist angle for small angles. And this would be the situation that would occur if electrons in two graphene sheets, they didn't know about the other graphene sheet. However, because these electrons, the two graphene sheets are only 3 angstroms apart, they can tunnel between these sheets, and this interlayer tunneling gives rise to, bonding anti-bonding states, okay? Very similar to a hydrogen molecule, but it's now a giant graphene molecule, okay? And this is the situation when this interlayer tunneling is small compared to the energy of this crossing point. But as you decrease the twist angle, this, this energy of these bonding states goes to lower and lower and lower energy until it reaches 0, okay? That flat band condition is reached at the magic angle, which is 1.1 degrees for magic angle graphene. And as I mentioned yesterday, there was very interesting single particle physics work, both theoretical and experimental, about a decade ago on the system. So then these flat bands, electrons in these flat bands, they like to localize, they like to be near regions of AA stacking. So this means that schematically, we have magic angle graphene. We have these regions of AA stacking where the electrons like to sit, and those are spaced about 13 nanometers, okay? And this is sort of the equivalent of cold atoms, from Hubbard lattice, except that because, of the interesting topological properties that, Andre already mentioned yesterday, it's a bit more, exotic and not, there's no a one-to-one mapping. Now, what my group discovered, already 3 years ago is that when you put your chemical potential in the flat bands of the system, there are regions where you can reach correlated insulator behavior, and there are regions nearby where you have an electrically tunable superconductor with many similarities to other correlated materials which exhibit superconductivity. Okay, this happens all in a relatively narrow range of twist angles around 1.1 degrees. So, okay, so this is what I told you about pretty much yesterday. Now, I want to go back to the phase diagram of graphene, okay? And then we'll slowly build towards. So if you have graphene, you have Dirac cones. Also, if you have large angle twisted bilayer graphene, okay, you have Dirac cones. This is an electronic structure for 3 degrees twist angle. As you can see, at low energies, it just looks like graphene. In a phase diagram, temperature versus density, there's only one relevant, one interesting region, which is the charge neutrality point. Okay, system is metallic everywhere. Charge neutrality is a little bit special and that's it. Now, if you go to small angle twisted bilayer graphene, not jet magic, small angle twisted bilayer graphene, the electronic structure starts to reconstruct substantially. This is for 1.8 degrees here. There is a set of Moire mini bands. They're not yet very flat, okay, but they're a little bit flattish. And there are already band gaps, single particle band gaps that appear that separate the central Moire mini band from the other remote mini bands, okay? Therefore, in this phase diagram here now, besides charge neutrality, because of this graphene-like, data cones, you also have, when your chemical potential is here or here, band insulators. And that occurs at 4 electrons or 4 holes per molar unit cell. Remember that we use this thing called filling factor, nu, to represent in a Moire superlattice the number of electrons or holes that you place per Moire unit cell in these central Moire mini bands, whether it's a flat band or like here, this Moire flattish mini bands, you can put 8 electrons per Moire unit cell in total, okay? This behavior at small but not magic twist angles was reported by my group already back in 2016, and related work by the group of Emmanuel Tutuk, in 2017 also. Now, if we go to magic angle graphene, okay, this is the phase diagram, temperature again versus filling factor. You have charge neutrality, you have band insulator when you chemical potential in this band gaps. Here is a flat band, okay, this is for 1.05 degrees. And now, as you feel these flat bands, you can see regions, near -2 and +2, okay? You have correlated insulated behavior, as I showed yesterday. And then if you dope away from it, you have superconducting domes. Whether you see all 4 of these domes or only 2 or only 1 depends on details, okay? And this was the situation roughly in the summer of 2018, okay? Now, I should mention also that correlated insulated work on ABC trilayer graphene on hexagonal boronitride was reported by the group of Feng Wan shortly after we reported our work. Now, this is the phase diagram from transport measurements, okay? And again, this is schematic, it's twist angle dependent, and it is evolving relatively fast, okay? But we have this, okay, in mid-2018, and then people started to find more and more things, okay? First thing is we saw a region of linear in temperature resistivity behavior, very reminiscent of the strange metal behavior in correlated systems. When that happens around the correlated insulated regions, okay? Then, whereas if you go to near charge neutrality, the system just exhibits the typical metallic behavior, let's say with a quadratic temperature dependence of the resistance. We also saw that the superconducting state exhibits nematicity, okay? It exhibits an anisotropy, and I'm gonna talk more about this today. We also saw that near top of the dome, okay, in the dome, we have competition between different orders, which tend to suppress superconductivity in certain regions. We also found that there is nematicity, so a breaking of rotational symmetry in the normal state of the system. Okay, so I'm going to be telling you about all this today. In addition, a lot of other physics happens at filling factors 1 and 3. So -1, -3. I will not be telling you too much about it. I will only tell you a little bit in the compressibility measurements, okay? But there's lots of interesting work by, many groups, including a lot of these things have been seen also by recent STM work. And, the field is very rich and this phase diagram is evolving faster and faster and faster, So it's really a very rich system. Okay, so with this introduction, this is the outline of what I want to be telling you about today. I'm going to start with an investigation of competing orders in magic angle graphene. Then I'll tell you about nematicity, both in superconducting and in the normal state. Then I'll tell you about our compressibility studies. So these represent the first measurements of thermodynamic properties of graphene, where we see a cascade of phase transitions and Dirac revival. Well, by now, this is a little bit old, this title actually. It's not Dirac revivals. It should be other type of revivals, but you'll see what I mean. And then I'll tell you about strange metal behavior in magic angle graphene. Okay, so what does the term competing or sometimes intertwined orders means. Okay, this has been mostly explored in many correlated materials, but explored perhaps more in depth in the cuprates. Okay, here you have the phase diagram, temperature versus doping for high temperature cupra superconductors. And as you can see, the superconducting dome, okay, here is not just a single dome. It has sort of two domes. There is a depletion here, okay? Now, in some cuprates, the depletion goes all the way, it makes TC go almost all the way to zero, like in here, like in, lanthanum barium copper oxide, okay? And this depletion of TC is associated with a competition, with a competing phase to superconductivity. In this case, it has to do with stripes, okay, stripes order, okay, which happens at the so-called 1/8. This is the 1/8 doping anomaly. Okay? So this is something that has been investigated a lot in the cuprates, and other materials also exhibit this type of competing phases between superconductivity and something else. Now let's look at right away at data in magic angle twisted walleye graphene. Okay? So this is a high temperature, high temperature in quotes, but let's say up to 20 Kelvin, much higher temperatures that I was showing yesterday, for a device 1.09 plus minus 0.02 degrees. Okay, this is the resistivity as a function of temperature, as a function of density. Okay, now as you can see, there are many features here. This is charge neutrality. This is the correlated insulator at 2 electrons per mole unit cell. This is 2 holes per mole unit cell. Something happens also at 1 and at 3. I'm not going to be telling you about much here. Here is the superconducting dome. Let me zoom in a little bit there. Okay, let me zoom in there. I zoom in. Okay, this is RXX again. This is temperature. This is charge density. Okay, let me zoom in. Well, before I zoom in, I want you to note, see that there is a resistance reach, we call it, or sometimes we call it a banana, because in this color scale, this looks yellow, okay? This is a maximum in resistance with respect to nearby regions in density, okay? And it looks like this. And as you can see, that, this dark blue here means superconductivity. You can see this superconducting dome exhibits a dip there, okay? So let me zoom in even more, okay? So remember, from the point of view of doping, this is the correlated insulator states for 2 holes per mole unit cell, which means in terms of extra doping, this corresponds to 0, okay? Filling factor -2. And in this direction, we add more holes to the system. And as you can see, we have a superconducting dome, which clearly shows 2 bumps, okay? And the depression here in TC seems to be related to this resistance reach, which we observed at higher temperature. Okay? Now, this, the moment I saw this, it reminded me again of these type of pictures. Okay, this is 0 doping lattice, so filling factor, 1 if you want, and then as you add holes, which in the cuprates they usually show it in this direction, you have this type of behavior with a double hump dome. Okay, so again, it was quite reminiscent, so we tried to look at it a bit more. One of the things that we did is we saw, okay, let's see what is really happening. Let's apply, this is a 0 magnetic field so that we can see the superconductivity. What happens if we apply a small perpendicular magnetic field so that we kill superconductivity, and we can see what is really trying to develop underneath here, okay? So we measure this data now at a small perpendicular magnetic field, half a Tesla, and then we can see that this resistance reach becomes an insulating state at low temperature, okay? In fact, if you measure at this density, okay, where we had the depletion in TC, we see that at 0 magnetic field, you have a superconducting state. At finite magnetic field, you have an insulating state at that precise density, okay? Right, so we saw this in one device. We thought, okay, let's see if we see it again. And these are data from another device, 1.0 degrees in this case. In this case, the correlated insulator state is barely visible, just a tiny feature here. And we have this banana, okay, this resistance reach, which happens there and creates a depletion in the superconducting dome. If we now apply a small perpendicular magnetic field, we can see that this resistance ridge connects to an insulating state at low temperatures, which is clearly separated from the correlated insulated state that occurs 2 holes per Moire unit cell. Okay, and again, if you measure your resistivity there versus temperature under both conditions, in one case you have a transition to superconducting state. In the other case, you have a transition to an insulating state. Okay? So this is something that we have observed, and of course, we can do these measurements that I just showed you at 2 different magnetic fields. We can do them continuously as a function of magnetic field. Okay, so this is, a plot of the critical temperature versus doping at, different, and I have superimposed here different perpendicular magnetic fields so that you can see that this original dome, which then exhibits a depletion there, eventually it separates into 2 domes, the superconducting dome, and then only the last remaining dome, the strongest, remains up to, a few hundred, millitesla. Yeah. Now, this, when we took this data, again, reminded me very much of data taken by, the group of by Brad Ramshaw, on high temperature Cooper superconductors, where you measure the TC versus hole doping. In this case, they have to use gigantic magnetic fields, up to 80 Tesla in order to measure this, but they basically saw a similar evolution with a small, perturbation on the TC, which then isolates the 2 domes, and only one last remaining dome survives. Of course, the big difference between this data is that, as you can see, here the actual data points are those few discrete data points that you see here, okay? Whereas here, all of these data points are continuous measurements, that we can take in this diagram, because we have full electronic control over our doping without the introduction of chemical impurities. Okay, so let me show you now a different aspect, okay, of correlated behavior in magic angle graphene, and that is nematicity. So nematicity means spontaneous breaking of lattice rotational symmetry of some order parameter. Okay, many families of quantum materials show this. The Nictide superconductors, the cuprates, heavily doped topological insulators, etc. This is something that can happen in the normal state, in the superconducting state, or in both, and it has different implications in each case. Yeah? In the Nictides, it has been very heavily studied in the normal state. For example, this is the phase diagram taken from the review by Rafael Fernandez. Temperature versus doping, this electron doping is hole doping, and you have these regions here of nematicity, okay, in the normal state. Okay, so breaking of lattice rotational symmetry in the normal state with nematic fluctuations above, and etc., and all kinds of very interesting behavior. In doped topological insulators, okay, there's an example where nematicity has been seen in the superconducting state. Okay, bismuth selenide has a hexagonal lattice structure, and what you can see here is that if people measure the resistivity as a function of, I believe in this case it was application of in-plane magnetic field, you can see that the critical temperature of the resistivity exhibits a 2-fold, okay, 2 maxima, between 0 and 360 degrees, which means 2-fold anisotropy in a hexagonal lattice, which should show either 6-fold or 3-fold, depending, exactly how you look at it. Okay, that reduction from, these, from hexagonal symmetry to 2-fold anisotropy. Okay, it's a, it tells you that the superconducting state in doped bismuth selenide is nematic. Yeah. Okay, so let's look at. Oh, I forgot to update this reference. This is the same science reference. I think you'll see it in different slides. So we take magic angle graphene, and what we do now is we apply. So okay, we measure at zero magnetic field. It exhibits superconductivity, a pretty high critical temperature for this device. Sharp voltage current characteristics, etc. And then what we do is we measure then the graphene, which, by the way, here is the superconducting dome in log scale now as a function of density. This is, by the way, one of those devices where we see a competition in orders here, okay, depletion of TC at a certain doping. And then what we can do now is we can measure the resistivity of the system as a function of in-plane magnetic field, okay? As a function of in-plane magnetic field direction and in-plane magnetic field magnitude, okay? So here you have your resistivity as a function of in-plane magnetic field direction at different magnitudes, okay? And what you can see is there is this twofold behavior, okay, of the resistivity, yeah? Now, what we can do, in fact, is do this, twofold, again, means an ellipse, okay, because it has two maxima. Let me show you the ellipse. This is the resistivity as a function of magnetic field in the x direction and in the y direction. And as you can see, there is this ellipse, okay? Here, blue means superconductivity, red means when it gets out of the superconducting state. And as you can see, the critical in-plane magnetic field has a different value in this direction and in this direction, okay? Hence this ellipse, okay? Now what we can do is we can look at all of this everywhere as a function of doping, okay? So if we go to the superconducting dome, we have here different points, okay? By these letters, then we can go here, and this is how the anisotropy evolves as a function of doping. This is at base temperature, okay? In some regions, this is at optimal doping. Turns out in our setup, we have a maximum 1 Tesla in-plane field. So at optimal doping, for example, below 1.7 Kelvin, we cannot detect any anisotropy because the critical field is too high in all directions. But if we increase the temperature, we can see the appearance of an ellipse, which then disappears in the normal state, okay? At this intermediate temperature of 0.9 Kelvin, we can look at the evolution of the ellipse with density, with doping, okay? So what you can see, this is quite complex, and you can go to this paper to look at all of the details. The only thing I want you to pay attention to or remember is that here the ellipse has sort of an axis which is sort of tilted in this direction up, maybe something like 20 degrees. Then we go through optimal doping. The ellipse here has changed, then it has rotated, then now it's pointing downwards, okay? So this ellipse axis, the major axis, okay, or your nematic axis is called, is changing with density, okay? Now, if it is changing with density, that means that it's highly unlikely that it will be just a result of pure strain, okay? Let's imagine that we have our magic angular field and we have stretched it very strongly in one direction. That would break the lattice rotational symmetry and make it, just choose a direction, okay? But because we see that with charge density, our nematic axis is, varying, that means that it's not just a result of a, very strong strain in the system, yeah? Now, let me leave it at that, the superconducting state. Let's look now at the normal state, and I'll come back to put everything together. So this is, the resistivity versus temperature and density, for the device. This is the banana. This is correlated insulator state at low temperatures. So that's filling factor -2. Here we have our banana with a depletion of TC. Now, this is a measurement of RXX, okay? Now, let's see what happens if we do a measurement of the transverse voltage, okay? The equivalent of the whole resistance, but at zero magnetic field, yeah? In principle, we would expect that measurement to give you 0. However, as you can see, there is a region of very strong RXY, okay, behavior. Okay, so let's look at this a bit more carefully. But first, let's think about why would you have, and by the way, the region where this RXY is very strong is the same region as where you have this resistive ridge, the banana, okay? So why would you have a transverse resistance at all, okay? Well, this is something which can happen for anisotropic materials, okay? So your resistivity tensor, okay, 2 dimensions, you have ρ1, 0, 0, ρ2, okay? This is, if your device axes are aligned with your crystallographic axis, okay, then you expect to measure 0 transverse resistivity, okay, if you measure transverse voltage here. Now, the thing is, when we fabricate a device in general, we don't know if our anisotropy axes are oriented in the same direction as the device that we etch, okay? Because we do not have information about the crystallographic orientation of our magic angle bilayer graphene, okay? So if you take the most generic case where you have an anisotropic material and now you make a device, okay, a whole bar on it, this, the whole bar axis will not be aligned with your anisotropic material, with your anisotropy axis. And then you have to do a rotation, transformation of your resistivity tensor. And in general, if you have anisotropy, if rho 1 is different from rho 2, okay, then you expect to have an RXY component in your system. Okay? So as long as the sine of 2 theta, sine theta cos theta, sine of 2 theta, the sine of 2 theta is not 0, okay, you expect to have a rho XY, which is proportional to your anisotropy, okay, to the resistance difference. Now, so at zero magnetic field, we measure RXY and we correct, because it can be various artifacts that can give you a finite value of RXY. We correct for all of those, and we have this very strong signal here in this region, okay? In fact, we can normalize RXY by RXX, which is proportional to rho 1 minus 2, rho 2 divided by rho 1 plus rho 2. And we can see that, there is a very strong, of order, 50%, anisotropy in the system in that region where we also see the resistivity reach, which leads to a competing phase, okay? Superconducting phase. So I should mention, by the way, that normal state nematicity has also been seen in recent STM work, by various groups. So this picture that is emerging, okay, in this, nematicity and competing order sort of schematic joint picture is the following, okay? In the phase diagram of magic angle graphene, temperature versus doping near the region filling factor -2, 2 holes per more unit cell. So at -2, so 0 doping, we have a correlated insulator behavior. Then we have a superconducting dome, okay? The superconducting dome experiences a depression at a doping of order 10%, okay? And that depression here coincides with a normal state resistivity reach, okay? Which if you suppress the superconducting dome leads to an insulated state here, okay? As I showed you, at finite magnetic field. Now, this region, okay, of resistivity that competes with superconductivity has normal state nematicity, anisotropy in the normal state. Now, the superconducting dome, everywhere in the phase diagram, you have also nematicity, okay? But the nematic axis can change direction, okay? In particular, the nematic axis seems to change direction weakly in this region, but then when it gets, when you dope into this region where we have this normal state nematicity and this competing phase, actually it changes rapidly there. So it seems that the superconducting state is nematic everywhere, but in the region where there is competition with this other nematic normal state phase, the system, the superconducting, or the parameter, its nematic axis aligns, gets set, by that, competing phase, which happens in this region, okay? So if you want more details, you can look about this paper. I'm happy to answer questions about it. Okay, so let me tell you now about our thermodynamic measurements, okay? And I'm only going to tell you a little bit because I want to have some time to go into strange metal behavior. So this is the phase diagram, a different version, but very similar to what I showed earlier. The phase diagram for magic angle twisted bilayer graphene, okay? Temperature here on this axis, filling factor, band insulator at 4 electrons and 4 holes per more unit cell when your chemical potential is in these single particle gaps. And then, as I mentioned, at each integer, something happened, okay? We had some signatures in transport of something happening. For example, correlated insulator at 2 and -2, very often also at 3, we see it. And then at 1 at -1, often a correlated semi-metal behavior. It's not an insulated behavior, but it's a resistance peak that occurs there. Here, this is rarely seen. This is quite frequently seen. And then at charge neutrality, you have a Dirac semi-metal, occasionally a Dirac insulator type state, okay? In this region, you have strange metal behavior, and then you also have some nematicity and all these other things that I just mentioned. Okay, this was all information that we had obtained from transport measurements. Okay, now what happens if you do thermodynamic measurements? Okay, that gives you different access to the physics of the system. Okay? So in particular, we work together with our collaborator Shahalilani at the Weizmann Institute. Okay, and similar work was reported by the group of Ali Yazdani and separately later on by us. We started to do measurements of the chemical potential of the system of graphene as a function of filling factor. Okay, so mu is the chemical potential. D and d mu, how does the charge density change in the system when you change the chemical potential? That is a quantity known as compressibility. And in the simplest case, okay, in single particle physics, the compressibility is just the density of states, okay, proportional to the density of states. The inverse compressibility, or how does your chemical potential change as you add charge to your system, that's known as the inverse compressibility. And again, in single particle physics, in the absence of interactions, that's just 1 over the density of states. Okay? So in this paper, we reported measurements of the inverse compressibility, d mu dm, as a function of filling factor, okay, for magic angle graphene. In fact, what the group of Shahalilani does is they have this very interesting technique where they have a carbon nanotube single electron transistor at the end of a tip, of an AFM tip, which they can scan on top of your sample. So we have a magic angle graphene sample, and locally they could go to different spots in the sample. You know, different regions have slightly different twist angles, so they could measure the inverse compressibility at all of these twist angles. Okay, so here you see this set of traces. The different colors correspond to different regions in the device where the twist angle varies slightly. You know, you start from 0.99 degrees. You see there are only 3 basic features, okay? A few others, but 3 features in the inverse compressibility as a function of filling factor. You have a peak at -4, a peak at 4, and a peak at 0. Again, because the inverse compressibility is like the inverse density of state, this is telling you that you have gaps at 4 and -4, and you have a Dirac point at 0. Yeah? But if you go, okay, if you go now to 1.3 degrees, okay, above the magic angle, you have the same features, okay? 3 peaks at 4, 0, -4. But if you go in between, in the magic angle range, let's explore here, for example, 1.13 degrees, you can see you have those peaks, but then you have also a whole bunch of other features, okay? Let me zoom in a bit more into those. So this is the inverse compressibility, the mu dn, as a function of filling factor. This is at 0 degrees for a region which has 1.13 degrees, okay? What you can see is this large peak corresponding to the gap at 4 and -4. Then we have also a peak corresponding to charge neutrality. And then we see that at each integer, there is this sawtooth type of behavior near each integer, okay? Turns out this sawtooth type of behavior, okay, represents a cascade of phase transitions, okay? A phase transition is taking place near each integer filling factor, okay? And to 0th order in the simplest, you know, model that we could, you know, come up to explain this data, what happens is that each of these phase transitions corresponds to a flavor polarization of the system, okay? And I believe, you know, either Andre or Oscar, you know, will mention, we'll talk about this in greater detail with a more sophisticated model than the one we initially chose to explain our data, okay? But let me just tell you, you know, in the simplest model, and you will hear from Oscar a more refined model. So if you know, remember that we have 4 flavors for electrons in graphene: spin up, spin down, valley K prime, okay? So initially, let's start from charge neutrality, okay? And this is the population of the 4 flavors as we vary the total filling factor, okay? Initially, all of these flavors get occupied at the same rate. When I add electrons to my system, I'm adding electrons to all of the 4 flavors, okay? Starting from charge neutrality. Okay? However, when I'm close to filling factor 1, so when I'm close to having added 1/4 of an electron to each flavor, 1 electron in total, 1/4 of an electron to each flavor, Due to strong interactions, the system decides it's energetically favorable to polarize and send all of the carriers to fill one flavor and empty the other 3 flavors. Okay, so then the population of one of the flavors goes up and the other 3 flavors goes down to 0. And then we start again. We start filling the 3 remaining flavors, okay, initially at the same rate. But then when you're close to filling factor 2, when you have about 1/3 of an electron in each of the 3 remaining flavors, the system again decides to spontaneously flavor polarize due to strong interactions and empty the other 2 flavors, etc. Okay, and this repeats itself. So as you can see, there is a cascade of flavor polarizing transitions in your system. In the simplest model, that gives you an inverse compressibility, which has a sawtooth type of behavior like this. Okay, and again, there are nowadays more sophisticated and more complete models that describe this behavior. Now, this means that in the phase diagram of magic angle graphene, okay, you have all of this correlated insulator behavior in superconducting domes, etc. But there is an overarching flavor symmetry broken parent state on top of which these correlated insulator states and superconductivity develop. Okay, and this flavor symmetry break, this cascade of phase transitions, I don't have time to show you the temperature dependence, but occurs already at temperatures of very high temperatures of the order of 50 Kelvin, 70 Kelvin even. Okay, I put here 30 Kelvin very conservatively. We have seen it happening, at even 70 Kelvin. Yeah, so that's something that should be in your minds as you look at magic angle graphene. Okay, system changes at the integers. So now in the last 10-15 minutes, let me tell you about strange metal behavior in magic angle graphene. Okay, now. What are strange metals? So the strange metal phase is characterized by strange behavior, hence the name. Okay, so behavior which is at odds with the conventional Fermi liquid behavior of many properties. Okay, and one which is most emblematic is the linear in temperature resistivity, all the way from low temperatures to very high temperatures, but it's particularly striking the fact that it goes all the way to very low temperatures. Okay. Some cases with a crossover to a conventional Fermi liquid behavior below some coherence temperature. Now, again, this is a behavior that many families of correlated materials show this: ruthenides, cobaltates, some pnictides, heavy fermions, cuprates, etc. Okay? So in this famous phase diagram of the cuprates, this is this big wedge above the optimal doping in the superconducting dome, in between the pseudogap phase and a more conventional Fermi liquid behavior in the overdoped region. Okay, so as you can see here in this diagram, this is data from the cuprates. If this is a function of doping, and there's a region of doping for which this behavior is very, very linear right there. Okay, whereas if you go, for example, here, it looks more, more quadratic behavior, etc. In the case of data on heavy fermions here, you can see resistivity versus temperature, linear all the way down to the absolute lowest temperature I could measure. Okay, so this is a very striking behavior. Now, in many strange metals, the scattering rate exhibits a sort of universal behavior. And Jensen speculated that there might be a Planckian bound on the scattering rate. That means the scattering rate, okay, reaches a value which is kBt over h bar times a coefficient, and this coefficient is of order 1. Okay. So this is something that was investigated, in many materials, and that put very nicely together by the group of Andy Mackenzie, okay, where they showed, in this, it's a complex way of showing it, but basically this straight line here is telling you that Planckian scattering rate, and you can see that many correlated materials, are roughly, have a scattering rate roughly on that edge, on that end. That range. Also, a number of uncorrelated materials, but at high temperatures also exhibit that behavior. Okay? Copper at high temperatures, for example, but not copper at low temperature. Okay. Now, in a more recent paper, the group of Louis Taillefer studied this in detail for a variety of cuprate superconductors, and also compared with some organic superconductors. Okay, and what they call alpha is what I call here C. Okay, it's coefficient for the the proportionality coefficient for the scattering rate and temperature, okay, with the fundamental constants, happens to be, as you see, it's not something that is perfectly quantized. It's not like quantum Hall physics, okay, but it's something that it was seen to be within 30–40% of 1, okay, in the system, okay, for a variety of systems. Okay, so let's look at magic angle graphene. So this is again a phase diagram that I showed you, before, and if we look in this region near the correlated insulator behaviors for 2 holes per more unit cell or for 2 electrons per more unit cell, and we measure the resistivity up to higher temperature, you can see this, okay? Here is for 1.09 degree sample at a filling factor of -2 minus delta, okay? So, close to optimal doping. You can see that once you get out of the superconducting state, the resistivity then is very linear with temperature, okay? And this is actually 25 Kelvin is very high temperature for the system because it is of the same order, okay? It's actually above the Fermi temperature of the system, okay? Remember, because we have a Moire superlattice, the densities that we're talking about in these systems are extremely low. So the Fermi temperature is very small. Now, if you choose a doping, and a sample, this is a 1.16 degree sample, the doping at +2 minus delta, very close to the tiny dome that we have here, okay? You can see that, superconductivity occurs only at extremely low temperatures, and then pretty much once you get out of superconductivity, you have this very, 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 very linear behavior, again, all the way to above the Fermi temperature, and it goes linear with the same slope, pretty much to 0. In this case, down to 0.5 Kelvin. I'm aware of recent data by the group of Dmitry Efetov, where he has seen this behavior by choosing a property sample and the dome, etc., going down to 40 millikelvin. Okay, so this is a behavior that is very, very unlike what you would expect for a conventional Fermi liquid. Okay? Now, you can study in the system again. One of the advantages of magic angle graphene compared to many other correlated systems is that we have continuous electronic control over the doping in our system. So if you look at the resistivity versus temperature at each of these dopings, the colors here correspond to color scale here, okay? You can see that this linear temperature behavior, the linearity is best, around the correlated insulator state, but it's also pretty much linear, all the way, around the range that encompasses both domes. Of course, once you get out of the superconducting state. So at low temperatures, you can have superconductivity, you can have metal insulator transition, all kind of correlated insulator behavior, all kinds of things. But then once you go above a certain coherent temperature, then your behavior is linear, and the slope is very weakly dependent on temperature. Okay, this is data for a 1.16 degree device around 2 holes per more unit cell. This is data for a different 1.16 degree device. Okay, it's just coincidence, it's the same angle, but it's a different device for data around 2 electrons per more unit cell, and you can see how linear and how weakly dependent, the temperature dependent, the slope can be. Okay, in the system, around this range. Now, so we can investigate both the slope, d rho dt for the system, okay, as well as the offset, okay. It turns out the resistivity slope, it can vary from tens to hundreds of ohms per Kelvin, okay. In the middle of this range is comparable to the cuprates. On the high end, like 300 ohms per Kelvin in some cases, it's actually quite a bit larger than the cuprates resistivity slope when you normalize by thickness. And it's several orders of magnitude higher than in monolayer graphene, okay? Within this magic angle range, we didn't observe a clear trend with twist angle, okay? But we explored only always devices which were within the magic angle range, devices that exhibited superconductivity, etc. Now, you can also see, other data by a group of Andrea Young and some early theoretical predictions. Now, that linear behavior was seen, within this density range. If we go, for example, to filling factor -1/2 here, in between charge neutrality and the first correlated regions, Or if we go to charge neutrality, you can see that the behavior is not linear at low temperature, it's sort of quadratic, okay? In fact, it's not exactly quadratic, it's a power law behavior. And this power law behavior is consistent with what was seen at high twist angle, okay, for, a small twist angle, but not magic, let's say 2, 3, 4 degrees twisted bilayer graphene, okay? Near charge neutrality, they see also this quadratic behavior, more conventional, metallic behavior. Now, for some devices which are very clean, we can actually measure the scattering rate, okay? So this coefficient happens to be, h bar over kb, and then, other fundamental constants, and then the charge density, the effective mass, and the slope, the rho dt, okay? So we can measure all three quantities, in particular, the effective mass through the temperature dependence of the Shinnecock-Has oscillations, okay? So we can measure this coefficient, okay? And we can measure this coefficient, Z, as a function of doping, again, because we can continuously change our doping, okay? And we see that, for, around, this is around the correlated insulated state for 2 holes. So 2 holes, so -2 plus delta, what we see is values of the coefficient C or alpha, if you want, which are, within 50% of 1, okay? For extra holes, okay, at -2 minus delta, this coefficient varies between 0.25 and 0.4, something like that, okay? So it's certainly within a factor of, 3 or so of this value of 1, this Planckian scattering rate, okay? And this is what we have for graphene. Now, there are different, possible explanations for this behavior, okay? In particular, if your system has, if your electrons are coupled to bosonic degrees of freedom, for example, phonons, you could exhibit, linear in temperature resistivity behavior. So 2 papers, that I'm aware of that discussed this was, possibility of linear in temperature resistivity by scattering by acoustic phonons, okay? And then also Moire pattern fluctuations and electron phase coupling, which is, similar different types of phonons, okay? This type of, theoretical models capture some qualitative features, in particular linear in temperature resistivity at high temperatures, but as you can see at low temperatures, it's always quadratic, okay? And in particular, it's quadratic at temperatures of the order of, 5, 10 Kelvin, where we see linear in temperature going down over an order of magnitude, or even 2 or 3 even orders of magnitude lower than that in temperature, okay? In addition, the scattering rates are typically underestimated with these mechanisms by between 1 and 3 orders of magnitude, okay? These models are typically also for graphene with renormalized Fermi velocity, but still linear band structure, not the complexity. They don't incorporate the complexity of the band structure of magic angle bilayer graphene. And also, they don't take into account that the phonon band structure for Moire structures is also gapped, okay? So these are calculations by Cochino and son on the phonon band structure as a function, so the phonon band structure, okay, energy and momentum. This is for no coupling between the 2 layers. This is for some coupling between the 2 layers at, in this case, twist angle 1.47 degrees. This is for magic angle bilayer graphene. And you can see there's a massive renormalization of the phonon band structure, including various gaps, okay? So you have a whole bunch of low energy optical phonons because of these gaps, okay, due to the coupling between the 2 graphene lattices. And in particular, the optical phonon energies at the magic angle are of order of a few millivolts with phonon gaps of a few millivolts. So we should see, okay, if phonons are playing a role in this linear T resistivity behavior, we should see a linear in T, but piecewise with the changing slopes as more phonons, more optical phonons get incorporated, into the behavior in this temperature range. But as you can see, it's the same slope from all the way from the above the Fermi temperature down to the lowest temperature possible without any kinks, okay? So this is something which, now most people believe that phonons do not play a dominant role in this behavior. So, a possibility is that, electron correlations are responsible for this. So there's some electronic origin for this. there is recent, a recent theory paper by Erisberg and collaborators on strange metals due to hot fermions. And this is something where Van Hoff singularities play a prominent role. And there are a number of papers that have shown that in magic angle graphene, you have special type of Van Hoff singularities called higher order Van Hoff singularities, extra strong Van Hoff singularities. Okay, so perhaps this is related. There is also a possibility that magnetic fluctuations, okay, are responsible for this. There are various people are now, theorists are investigating this behavior. Now, let me tell you something that we did, okay, and that mostly because a lot of theories were always asking me this question, So I would show this resistivity data and this strange metal behavior, and they would ask me, have you measured the diffusivity of the system? Okay, so it turns out that there is this general Einstein relation, okay, which relates the conductivity, or here inverse resistivity of your system, the compressibility, and the diffusivity. Okay, so it's just like this. Okay, your conductivity is equal to E squared times your compressibility and diffusivity. So if you have linear in T resistivity, that can mean several things. For example, your inverse compressibility is linear in temperature and your diffusivity is constant, or your inverse diffusivity is linear in temperature and your compressibility is constant, or combinations of these, etc. Okay, so essentially this quantity, the electronic diffusivity of a system, had never been measured in solid state, to the best of my knowledge. Okay, the only measurement where people did measure the compressibility and the diffusivity at the same time, hence they could measure also through the product resistivity, is for systems of ultra cold atoms recently. Okay, so we started to do these measurements now. Okay, so and for that we used a novel technique, okay, that was developed by the group of Emmanuel to measure the chemical potential of graphene initially. Okay, but now we adopted it to measure the chemical potential of magic angle bilayer graphene. Yeah? So what we have is the following. We have magic angle bilayer graphene, okay? And we have nearby, okay, there is an insulator here in between, and we have nearby a monolayer graphene. It's going to be a sensor. This monolayer graphene is going to be a sensor of the chemical potential in the magic angle bilayer graphene, okay? And we have a top gate and a back gate so that we can control the charge density in each of these layers, and hence the chemical potential in each of these layers independently, okay? This is the band alignment diagram. We have the back gate, top gate. We have the magic angle twisted bilayer graphene with Van Hoff singularities, flat bands. And here is the density of states of monolayer graphene, okay? This is the density of states of magic angle twisted bilayer graphene. So turns out, okay, and you can look at for the details of this paper. If you monitor RXX, the resistivity of magic angle twisted bilayer graphene, that gives you information about the chemical potential in monolayer graphene. And if you monitor the resistivity of monolayer graphene, that gives you information about the chemical potential of magic angle twisted bilayer graphene. Okay. The device structure, as I said, this is an optical picture. These devices are quite complicated, but you have backgate, hexagonal nitride, magic angle graphene, a 1 nanometer or so, 2 nanometers HBM, then the graphene sensor, then again, hexagonal nitride, and the top gate. Okay? So this is the resistivity of the monolayer graphene as a function of charge density in the monolayer graphene. It's a very high quality graphene sensor with a field effect mobility much higher than many hundred thousands, okay, with onset of silicon that has oscillations at 30 millitesla. Now, this is the resistivity as a function of density in the magic angle graphene as a function of temperature. You can see, charge neutrality, something happened on Philip factor 1, on Philip factor 2, Philip factor 3, superconducting domes, all of the beautiful things that I showed you before, okay? This is a device with a pretty high TC, 2.7 Kelvin. So let's check that this chemical potential measurement story works, okay? And for that, okay, I'm giving you here this equation now. If you chart, if you track the monolayer graphene charge neutrality, okay? So if you make, through the top combination of top gate and back gate, you make sure the monolayer graphene is at charge neutrality, zero density, okay? And you track that resistivity, then your magic angle bilayer graphene charge density is given by this formula, and the chemical potential of your magic angle bilayer graphene is given by this formula, okay? And again, for the derivation of these equations, you can check there, okay? The fact that the monolayer graphene is at zero at charge neutrality means its density is zero and its chemical potential is zero. So let's do a calibration test, okay? So magic angle bilayer graphene is a complicated object. Let's make sure we can use the scheme to measure monolayer graphene where we know what the answer should be, okay? So we're going to measure the chemical potential of the monolayer graphene using magic angle bilayer graphene first, okay? So what you can see here are the resistivity of the monolayer graphene in purple and the resistivity of the magic angle bilayer graphene in orange, okay? So if we track the charge neutrality of the magic angle bilayer graphene, this is giving us, through the equation that I showed earlier, the chemical potential of the monolayer graphene. If we do this in a magnetic field, okay, this will give us the chemical potential in a magnetic field. And indeed, okay, this, you can see that there is a, I don't know if you can see it because it's so perfectly on top. There's a white line on top here. This is just the chemical potential of monolayer graphene where we fit the Fermi velocity and we find a Fermi velocity of 1.12 10 to the 6, which is exactly, the Fermi velocity of graphene. And you can see that it exhibits this Dirac behavior, okay? Square root behavior here in density. The same thing for, in the presence of a magnetic field, we have this BF times square root of magnetic field and random level index, okay? So this works very well, this technique. Now let's do the opposite. Let's track the monolayer graphene, okay? In order to measure the chemical potential in the magic angle bilayer graphene. And this is what you can see here. This is the resistivity of the monolayer graphene, okay? And you can see that there is these oscillations like this, okay? So we can extract the chemical potential both as a function of temperature and also as a function of magnetic field. Very interestingly, through these chemical potential measurements and through Maxwell's relations, we can extract the entropy of the system, the magnetization of the system, the magnetization of the system is shown here, etc. Okay? But this is a technique basically that allows us to measure, in this case now, the compressibility, okay, the chemical potential, but as a function of density. So we can also take the derivative, d mu dn, and we can do it as a function of temperature. So we can extract now the compressibility as a function of temperature. We can also measure the resistivity as a function of temperature. Hence, we can do the first measurement in the solid state of the diffusivity, the electronic diffusivity as a function of temperature, okay? So, and by the way, one other thing that I wanted to tell you, as you can see in these chemical potential measurements, the derivative, you can imagine what the derivative of this looks like, okay? It looks like those peaks, okay? In the inverse compressibility measurements that I showed you in our work with Shah Halilani. As you can see, something happens at each integer, okay? Again, a cascade of phase transitions. This cascade of phase transitions is telling you again that before and after the correlated insulator states, the systems are very different, okay? Because it has been a phase transition in between, okay? Okay, so in this device, we can measure the resistivity as a function of temperature all the way up to 70 Kelvin, okay? So this is resistivity for selected traces here, okay? You can see it exhibits a, near nu equals 2, where the correlated insulator state is very linear, okay? You can see it's perfectly linear, okay? Down to a temperature at which the correlated insulator takes place. Then we go to regions nearby where it's, goes down in resistivity because it's in proximity to superconductivity, etc. I'm trying to avoid here the superconducting regions and regions also which exhibit negative compressibility, as I will show later, okay? But you can see that it's linear or slightly sublinear behavior, okay? But very unlike what you expect from Fermi liquid behavior. Then we can measure the inverse compressibility, okay? By measuring the chemical potential as a function of density and its derivative, then as a function of temperature. There's some regions with negative compressibility, which are due to correlations. I'm showing you traces here, trying to avoid that, negative inverse compressibility, because that's something which has nothing to do with strange metal behavior at higher temperatures. Okay, so you can see this is the inverse compressibility, this is a function of temperature, and you can see that it's relatively weakly temperature dependent. Okay, so then I can put these two together and measure the inverse diffusivity. Okay, in this case, just to give you some details, it's a D star, so I'm subtracting the offset in the resistivity. Okay, but by putting together resistivity data and the inverse compressibility data, we have the inverse diffusivity. And as you can see, okay, the major contribution, okay, to the linear resistivity in temperature comes from the linear behavior in temperature of the inverse diffusivity. The compressibility has a relatively weak temperature dependence. Okay, so just to give you an idea, there is also a bound on the diffusivity given by fundamental constants and also VF and T, okay, which is up here, we are below that bound. So you have here all three data together, okay, for you to look at. These are the first measurements of the electronic diffusivity in a solid state system by combining resistivity and compressibility measurements, and this is what we recently reported. Okay, with this, because I think I'm already out of time, again, acknowledgements to my group members, funding agencies, and thank you all for your attention.
Thank you, Pablo. Thank you for this beautiful talk. We have time for a couple of questions. Actually, there is one in the Slack channel, question from yesterday. Juan Hernandez Tecorralco is asking whether the flat bands in magic angle Bailey graphene could be related or be evidence of ferromagnetism in this system.
Well, I would say I would phrase it in a different way. Okay, when you have a flat band, there's competition between kinetic and interaction energy. Okay, and hence, in the limit where your bands are very, very flat, okay, interactions dominate completely, and hence flat bands are typically fertile ground to have various types of ferromagnetism, because now your interaction energy dominates over your kinetic energy. So for the system is, it can be favorable to polarize, okay, and it can be ferromagnetic in the sense of spin ferromagnetism, but it can be also ferromagnetic along a different flavor. Okay, so flavor polarization. So indeed, that's something that happens in flat band systems, and it happens also in magic angle Bailey graphene.
Thank you. Another question in the Q&A box: is it known the flavor polarization for all the integer fillings? For example, what is the flavor polarization at the superconducting phase Bailey or spin polarization?
Mm-hmm. Yes, this is something that is not known precisely experimentally. Okay, we have or not known for all filling factors. Let's say for filling factor 3, when you have only one flavor left, okay, people have seen that this flavor seems to be spin and Bailey polarized. You have only one flavor left, so that's sort of easy. Okay, but for example, the situation for filling factor 2, which is the most one of the most interesting, because it's around which superconductivity occurs and also strong correlated insulator, etc. We do not know yet if the system is spin polarized, flavor polarized, spin Bailey locked, or other types of possibilities. Okay, there's several of them, and theories have an opinion, and you may hear from Oscar about what is the many body ground state that he thinks is present at filling factor 2 or -2 for the correlated insulator state, and then by doping that state, what type of superconducting behavior emerges. I don't think we have a definitive experimental confirmation of what's the flavor polarization for 2.
Okay. Okay, thank you. I have actually a question. Am I allowed to ask questions?
I'm sure you are.
Okay, so it's a brief question. I mean, you mentioned part of your talk about the competing orders, nematic order, and superconductivity. Do you have any evidence for broken translational symmetries there, like charge density wave, or whether the nematic order is a precursor of any broken translational symmetry?
Very interesting question. So in a different experiment, in different samples than those where I showed the nematicity, with our collaborator, with Amir Jacobi, We have
Mhm.
states in magic angle bilayer graphene, which was probably not exactly, but partly, you know, a little bit aligned to HVN. Okay, with a small twist angle, with a small angle with respect to the HVN substrate, we have seen evidence for charge-sensitive wave states. People that do STM experiments, like I believe the group of Eva and Dre, they have seen also some evidence, or Abhay Pasupati, I forgot which of the two, it could be the both of them. They have seen some evidence also for charge-sensitive waves in the system.
Mhm. Okay, thank you. Thank you again, Pablo. Hope to see you tomorrow again. And let's thank
Thank
the
you,
speaker.
everyone.